going to talk about absolute convergence and conditional convergence. First, let's define that. Absolute convergence. We say that the summation of AN is absolute convergence if the summation of AN converges. Actually, we say it's absolutely convergent if the summation of AN, the absolute value of AN converges. Okay, the second one is conditional convergence. Conditional convergence. What does that mean? Summation of A sub n is conditionally converges if the summation of AN converges, but not the summation of the absolute value of AN. The summation of AN is conditionally convergent if, well, I said it's convergent, so if the summation of AN is convergent, but the summation of the absolute value is not. That is, the summation of the absolute value of A sub n diverges. Okay. Now, we have this theorem that states the following. If the summation of AN converges, then the summation of AN does. Summation of AN also converges. So if the absolute value converges, then A sub n converges. Okay. So we have that one. And let me just think for a moment, please. I just want to have this in front of me. I have to look it up. Okay. So we have to do some problems with these theorems and these definitions. Do a few of these and we'll move on. Okay, so I'm going to give you a series, and the problem asks to find if it's conditional convergent or absolute convergence. So we have the summation of -1 to the n plus 1 divided by n to the 1.5. That is, we have the summation of negative 1 to the n plus 1 times 1 over n to the 1.5. So what we need to do is consider this one. Consider this one. Does this converge? Does that converge? Now that's clearly our p-series, and we're going to use the test from the p-series to determine if it converges. Now, since n goes from 1 to infinity, n goes from 1 to infinity, n goes from 1 to infinity. Okay. So now, since p is 1.5, we know that it converges because p is bigger than 1. This converges. So we know that. It's probably best to find out which one converges and which one does not. Now, we can look at the summation. So now, what we really did was, what I really did, and let me be very clear about this, what I did was, I took the negative 1 to the n plus 1 times 1 over n to the 1.5, or even just n over 1.5. Let me erase this. I took the absolute value of this. I took the absolute value of that. And what I got was the summation as n goes from 1 to infinity of negative 1 to the n plus 1. That makes the signs alternate. But if you take the absolute value, it'll always be positive. So that is negative 1 to a power, the absolute value of that. That's just 1. So I have 1 over 1.5, and this converges by the p-series test. This converges. That is, the absolute value converges. Okay. So now, if the absolute value converges, let me erase just this little box. If the absolute value converges, this implies that the original one, the summation of negative 1 to the n plus 1 over n to the 1.5 converges by their theorem. If the absolute value converges, then the non-absolute value must converge. Okay. So they both converge. So then what we say is that a sub n is absolutely convergent. We say the summation of 1 over n raised to the 1.5 is absolutely convergent. We say that it's absolutely convergent. Okay, let's look at another problem. Let us consider this problem. Let's revisit their alternating harmonic sequence. The summation of negative 1 to the n plus 1 over n. N starts at 1. Does this converge or not? Well, actually, the real question is this. The real question is this one. You always look at the positive one. Okay? Is this absolutely convergent or conditionally convergent? That's the question. So what you want to do is the following. You know that the summation of 1 over n diverges. You know that the summation of 1 over n diverges. That's a theorem that your teacher should have proved. And now, if you look at the alternating sequence, alternating harmonic, we know that this converges. Okay, we showed this earlier. You need to know these two like you know your name. Whether you can prove it or not, you need to know that. Now, remember, to show that an alternating series converges, ignore the alternating part. Just look out the a sub n. In this case, 1 over n. And the next term will be 1 over n plus 1. The earlier term has to be greater than or equal to the next term. And that's true. And that's step 1. Condition 0 is that all the terms are positive. All the a sub n's are positive. And that's true. And the next one is the limit as n goes to infinity of 1 over n must be 0. Okay, that is, and since it is 0, it converges. That's the alternating series test for convergence. And since all 3 or 2 criteria have been met, we say it converges. Now, when is it conditionally convergent? What we have is that the alternating one converges, but the absolute value does not. If you take the absolute value of this, you get 1 over n. Actually, the problem should have asked this, sorry. You're asking if an alternating series is absolutely convergent or conditionally convergent. Or does it just diverge? Okay, so now, since the alternating converge, but the absolute value diverge, we say that is conditionally convergent. It's under condition whether or not we alternate the signs or not. Okay, let's try another one. Is the following absolutely or conditionally convergent? That is the question. So we have the summation -1 to the n times n divided by n squared minus 1. And n starts at 2. You can't start at 1 because 1 squared is 1, take away 1 is 0. You'd have, I don't know if it's plus or minus, but you'd have plus minus 1 over 0. Actually, we have minus 1 over 0. Okay, so the question is this conditionally convergent or absolutely convergent? So since they're asking which one is it, we'll assume that this converges. You would prove that by using the comparison test, the limit comparison test. Well, actually, since that's not true, that would be if it were an alternating. You would make sure that it's decreasing and make sure that the limit goes to 0. Okay, so now we'll assume it converges. Is it absolutely convergent then? That's what we want to know. Well, so we take the summation, we just ignore this. The summation of n over n squared minus 1, n goes from 2 to infinity. Does this converge or not? That's the absolute value of this mess? Does this converge? This looks like a 1 over n. When the terms start getting really, really big, like 100 billion, 20 trillion, these are approximately n divided by n squared. Taking away the 1 from 100 billion squared is insignificant. But that's exactly 1 over n. When the terms start getting really big, it starts looking like 1 over n. Now, I want to be clear on something. It's when a series diverges, it's not because of the beginning terms. It's always the tail end. Think about it. If you have 1 over 1 plus 1 over 2 plus 1 over 3 all the way up to 1 over 10 million or 10,000, all the way up to 1 over 3 billion, and then 1 over 3 billion plus 1, etc. I don't care how large this will be. I don't care how large that'll be. It's finite. You add up a finite number of numbers, like 3 billion numbers. You might get really big, you might get really small, but it won't be infinite. But we know that this equals infinity. It's because the tail end is infinity. It's always the tail end that makes it converge or diverge. It's not the first terms. So if the terms, when n is really, really large, start behaving like 1 over n, it's going to diverge. And I'm going to use the limit comparison test with 1 over n to prove that. We know that 1 over n diverges. The summation of 1 over n diverges. So I'm going to compare it. I'm going to compute right over here the limit as n goes to infinity of n divided by n squared minus 1. One series divided by the other one, 1 over n. And I know 1 over n diverges. If you don't know the convergence or divergence of what you're comparing it with, you're in deep trouble. Okay, so instead of dividing by 1 over n, you multiply by n over 1. And what that gives you is n times n is n squared divided by n squared minus 1 times 1 is n squared minus 1. In limits at infinity, you look for the highest powers in the top and the bottom. And if they're both the same, and they are, they're both squares, divide the numbers in front. You get 1 over 1, which is 1, which is positive and finite. That implies that they both converge or diverge. But since 1 over n diverge, they both diverge. This diverges. Okay? That tells me that the top one is conditionally convergent. Only the alternating converges, not the absolute. Just conditionally converges. If they tell you, is this alternating series absolutely convergent or conditionally convergent, it's reasonably to assume that it converges. Because if it absolutely converges, that means it converges. If the alternating converges. If they say, is this alternating series conditionally convergent? Well, then it must converge. Conditionally convergent means the alternating converges, but not the absolute value. That is not where all the terms are being added. They're telling you that the absolute one converges. And if they're not, they're tricking you. They're lying. Okay, that completes this. Next section will be the ratio and the root test.